Good afternoon, and welcome to the introduction to the energy model. So let's start off with the equations that we have on our equation sheet. There are 4 of them shown on this page right here, and there are some definitions to the right for some of the things we're going to do. There's another one for work. Work we're actually going to cover on the second day of the unit, not on the first day of the unit. So that although this is given to you, I won't be covering it too much today at all. These ones I will be talking about today. Let's start off with kinetic energy. So kinetic energy is the energy of motion. And so K is kinetic energy. And it is defined as 1/2 times the mass times the velocity squared. So the object must be moving in order to have kinetic energy. There are 2 types of kinetic energy. There's translational and there's rotational. We're actually going to cover rotational later on. And so although I'm introducing it here, my AP likes to cover rotational at the end. And so I'm going to kind of skip that. I'll introduce the idea right here, is when an object is revolving or rotating. And that's rotational. Anyways, we'll talk about what this symbol is for angular velocity later. So right now we're gonna focus on translational, which is this one. And then secondly, we have the idea of gravitational potential energy. So if I have an object that's held at a height and I drop it, is going to turn into kinetic energy, which means it has potential energy. And that is defined as the change in potential energy, which is a capital U, and then the letter G, is equal to mass times gravity, which is the object's weight, times its change in position. Sometimes you'll just see that written as mgh. So gravitational potential energy, GPE, is mgh. Potential energy kind of comes in 2 forms here, right? The second form is elastic potential energy, and it's the energy stored in a spring. And you'll see that this equation looks an awful lot like the first equation. It's similar in form, but the U, the energy stored in a spring, is 1/2 times K times x squared, where K is the spring constant, which basically means how strong the spring is. The larger the spring constant, the more resistive force it has when you squeeze it, or actually when you pull it. There's 2 types of springs. You can compress some springs, or you can pull some springs. And then the X is the delta X of which you compress the spring, the distance with which you compress the spring. And so energy can be stored in this spring. And then we have work, and we'll talk more about work later. James Prescott Joule is a dude you guys need to know, and that is capitalized for the unit. The energy units are joules. Newton was capitalized because Newton is a person, and James Prescott Joule is also a person. So joules are all energy units, and just as newtons are all force units. So in the end, we have something called mechanical energy, which is similar to total energy. So when we add up all of the energies, kinetic energy, gravitational potential energy, and elastic potential energy, you get mechanical energy, which is kind of the total of them. And we'll see how that applies in a little bit. Okay, so just basically speaking, here is a 2-kilogram car. It's moving 3 meters per second. K equals 1/2 mv squared. So 1/2 times the mass times the velocity squared gives you 9.0 joules. Okay, next we have a cart, which is going along a roller coaster of sorts, and the gravitational potential energy at any one point is mgh, but when we have a change of gravitational potential energy, we compare one point to the next. This is kind of a weird type of a situation, because if you can notice that it goes from 2 meters down to 0 and then back up to 1. So you got to be careful where the person who is asking the question is referring to, because if I call this point 1 and point 2, then there's a delta y, a change in height of 2 meters. But if I call it from point 1, and this is point 2, and I say from point 1 to point 3, then it's only a -1 change in displacement of y. And vice versa. If I go from 0 up to 1, then it's a positive 1. So it's arbitrary, meaning that the delta y really depends on where you're talking about from beginning to end. So this change in position, change in gravitational potential energy, has to do with how you're referring to it. And so mg times h minus ho, or y minus yo, or we could say is final position compared to initial position. Okay, anyways, what is gravitational potential energy of the 2 kilogram car when it is 1 meter above ground level? So this is where it was there. That's not what we're talking about. We're talking about right here. So when it is 1 meter above ground level, it has the potential to fall 1 meter. And so the gravitational potential energy is going to be 2 kilograms times 9.8, which gives us the weight times the height. And later on, you'll see why we're talking about sometimes from beginning to end. Right now, we're talking about just at this point. Okay. And then finally, and this is not the end of the video notes, I'm going to go farther today. Finally, we have elastic potential energy. So how much elastic potential energy is stored in this system when 2 kilogram car is pushed 0.3 meters, 0.03 meters into the spring that is a spring constant of 100 Newton meters. And if you notice, this distance is the distance that it is going to be compressed, and there is no mass considered in this equation. It is just talking about the energy stored in the spring. So it is going to be 1/2 times the spring constant times the distance you compress it, and you square it, and you get 0.045 joules. Okay, so pretty straightforward. Now let's move on to how we kind of like talk about the law of conservation of energy. And the law of conservation of energy says energy can either be created or destroyed, but it can change forms. And so let's see how it kind of applies to that situation. So in the energy model, we have energy as the ability to change the environment. It's a pretty vague explanation, but you'll see as we work through this, what does that actually mean? So the steps are to draw a picture, draw bar graphs, define the system, make an energy statement of conservation of energy, what goes in, what goes out, write your equations, and solve for your unknowns. And there's an updated version of this that I'll probably have for you in the notes. Same idea, a little more specific. So for instance, in this system, there is potential energy and there's kinetic energy that we can talk about, and mechanical energy is the total of all of them. And later on, we'll see that the idea of work is when you either add something from the outside or take work out of a system, and it doesn't really make any sense until you really put a practical application of that. So we'll talk about work next class. Right now, we're really talking about just within the system. Okay, first example, roller coaster part 1. So it says draw a picture. You got your picture here. Draw your bar graphs. And so here's my bar graphs. And so let's just start with that. So this system, and I have a little circle here, is going to include the car, the track, and the earth. And we have this picture of whatever's going on. And it says, what is the velocity of the car when it gets to the 1 meter high hill? And so this is why it's important to know. So where did the velocity come from? Well, it certainly didn't come from down here. We're not talking about a car with gasoline. We're talking about a cart, like a physics cart. And so it's at the top of this roller coaster, which is 2 meters high. It is going to go down, and obviously it's going to zoom down fast. And then here it's going to have some speed, and it will go up to the top of this hill, and it will have enough speed to go over the hill. And that's because of how high it was in the beginning. So exactly how fast will it be going? And we'll take a look at this as a frictionless hill to begin with, at least. So these are our 2 graphs. And the graph is basically saying the law of conservation of energy. So if the law of conservation of energy says the energy is neither created nor destroyed, what it means is that the energy that we have on the left side of the graph here, which is the beginning of the situation, is going to be equal to mathematically whatever we have on the right side of the graph. And so these are the different types of energies that we have. Remember that the kinetic rotational we're really not going to study right now. So all we really need to worry about at this point is energy stored in a spring gravitational energy or kinetic energy. And at the beginning, what we really have is just gravitational potential energy. And so this is kind of arbitrary as well. The one block or two blocks on your graph is just a way to generally say that however many blocks I have on the left, and I have two here, it must be equal to however many blocks I end up on the right because of the law of conservation of energy. So whatever energy I have represented in this graph, you can put it in different spots over here, but it has to have the same total amount. And there's two ways I'm going to draw this. I'm going to give you two examples, and there's two ways I'm going to draw it. So in the first example, I'm showing you with two blocks, and the reason this is crossed out because that's referring to my second example. So, okay. So what do we have at the beginning? We have two blocks energy, two blocks of energy worth of gravitational potential energy at the beginning. And at the end, over here, we have one block of gravitational potential energy because it's above the ground. And we have one block of kinetic energy. Now, is this to scale? No, it's not to scale. We could make it to scale. We could do some math, figure it out, and actually make it to scale. But right now, it's just symbolic more than anything else. So the same amount before, the same amount after. So mathematically, what do we have in this first case? On the dotted line below, it shows it on the second scenario. We're just talking about the first scenario, which is right here. The second scenario actually talks about it, and it really just basically says, don't go to the ground, then back up. Right? It says only consider the first point and the second point, and it's the exact same result. There's no difference between the results. It's just a different way to do it. So let's just concentrate on the first one first. So at the beginning, the initial gravitational potential energy can be just defined as mgy, not delta y because it hasn't changed. It's just a potential energy that it has. So it is 1 kilogram at 9.8 gravity, which because it's on Earth, so that's 9.8 times 2. And that gives me my initial state of gravity, which is this right here. And then in the end, we're going to have a little bit of gravity and a little bit of motion. And I don't know exactly what they are yet, so let's figure it out. How much are they? So the gravity they have, now that it's 1 meter high, will be equal to 1 times 9.8 times 1. 1 kilogram, 9.8 times 1. And then the leftover is what we don't know. We don't know how much is left for velocity. And so we know the mass, but we don't know the v. So the only unknown in this situation is this v squared. And so if we solve for v squared, we're going to get 4.43 meters per second if you just solve that out. So this is basically going to be 19.6 minus 9.8 times 2, and then take the square root, and you're going to get 4.43 meter per second. That's not hard algebra. Okay. The other way we can do it, as it says in this one, is let's not talk about it going down. Let's just talk about the difference between this point and this point. Let's just talk about the difference between that point and that point. So the way you would do that is you would basically say, I'm just going to use one block in this case. So I have one block of gravitational, right? And all that delta y, which is 1 meter, is going to go into translational. Is going to go directly into speed. It's just a different way to say it. I'm not even thinking about what happens down here, basically, because it doesn't matter. The truth of the matter, it doesn't really matter what happens between there and there because it's frictionless. If there was friction in the ramp, it actually would matter. But since it's frictionless, the speed when it goes all the way down and all the way up would be the same as if this just traveled in a straight line to there. It would be exactly the same. It would not matter because it's frictionless. So that 1 equals that 1. It could be 2 equals 2. It doesn't really matter. But the 1 really is basically saying that it's 1 meter, 2 meters. It's not perfectly to scale, but whatever. Okay. Actually, it is kind of scale here, isn't it? So anyways, so in this case, you would just have, I didn't draw the notes right there. This one, you would just have, you wouldn't have anything here. So there'd be none there. Why? Because that's the way it's drawn, right? It's just only considering from there to there. And then in the end, you would solve for v. Now, what do we get? We get the exact same answer. Why? Because this is 1 times 9.8 times 1, which is the same thing as 19.6 minus 9.8. What do you get? You get 9.8. It's the same thing. You times it by 2 when you take the square root, and you get 4.43 meters per second. So it's just basically showing you the same, how to solve it in 2 different ways. Okay, that's part 2. Now we're going on to the example of the spring. So in this example, all we're doing is we're dropping the ball this distance of 1 meter, but we're wondering how fast it'll be going the instant before it hits the spring. So when it drops this 1 meter, how fast will it be going? So what we have here is the idea that I have gravitational potential energy, which is here. I'm going to drop 1 meter, gravitational potential energy there. And as it drops here and it hits the spring is going to, sorry, it's not going to hit the spring. As it drops, it's going to gain speed. So the gravitational potential energy will turn into kinetic energy. So here we have gravitational potential energy, mgy or mgh, will be turned into speed. So why is it only, since gravity actually goes all the way down to there, why are we only considering this 1 meter distance? It's because that is all the question is actually asking. The question is just asking from there to there, how much height will it have covered? It will have covered 1 meter. And so how fast will it be going at the end of this 1 meter? Then we just do this. mgy equals 1/2 mv squared. We solve for v, and we find out how fast it'll be going. Okay, part 2 of this same spring example now says, what about when it compresses it? How much will it actually compress the spring, and how fast will it be going when it compresses the spring by 0.05 meters? So in this scenario, we're going just free fall to here, and then once we get here, we're going to contact the spring, and we're going to press the spring down, and we're going to slow down a little bit now because the spring is acting like your knees are flexing, right? You've landed on the ground now, and your knees are like a spring, and it's slowing you down, right? So instead of the total change in position from this point to this point being 1, the change in position is going to be 1.05, right? And it's going to squeeze this spring a little bit. So how do you solve this problem? Same idea. In the beginning, we have gravitational potential energy. And in the end, we have the spring is squeezed down, and we have the translational kinetic energy as well. So the delta y is going to be this much. It's going to be 1.05. And then the speed is still going to be 1/2 mv squared. And the energy stored in the spring is going to be US, and this is going to be 1/2 times k times s squared, and it is going to depend on the spring constant. And I will come back and I will talk a little bit more on this question in a moment. No, I won't. I will just finish it off right here. Okay, so in the end, we got another question, and the question has to do with this roller coaster and spring put together. So at the beginning, I am going to go actually my height from here to there. I'm not going to drop exactly 1 meter. I'm going to drop actually from here to here. I'm going to drop 0.95 meters. As you can see right here, we go from 1 to 0.05. And so from here to here, my delta y is 0.95 meters. And my spring, which I have a constant, is squeezed to give me, squeezed by 0.01 meter. And it has a spring strength K of 200 newtons per meter. And so I can take a look at this. What is the velocity of the car when it gets to the 0.05 meter hill? So it's a little bit of both these questions, right? And so what we have here is at the beginning, we have our energy, all of our energies. We have the energy stored in a spring. And remember, we don't need to really consider this little bit. And so that's kind of why that's cut out, and why that's cut out, because we're not going to go down and then back up. It's much easier to solve this question by not considering this height, but considering this height instead. So we have that height and this much spring power, and in the end, it's all of it turned into kinetic energy right there. All of these three things is turned all into kinetic energy. So you could write it like this, and you could solve it just like this if you want to. And that portion right there is going to cancel out part of that, right? It's not exactly an equal portion though. So it's not like 1 and then a half a meter. It's only a very small portion of it. So it's definitely not drawn to scale. Anyways, the easiest way to look at it is this is the spring and this is the gravity, which travels this distance, vertical distance 0.95, and that will translate into a kinetic energy. And of course, this would be 1/2 kx squared plus mg delta y equals 1/2 mv squared, and you solve for v. And now we can actually take a look at this with respect to a quiz and do the quiz and see if we can figure it out.